All right. So let's turn our attention now to the last topic that we'll cover in this course, which is electromagnetic waves, and we'll focus on light. So we've talked about the electric field and the magnetic field, and we've talked about the fact that if you have a moving charge through space, that a magnetic field forms around it. And it always forms perpendicular to it. And so imagine now that this charge is vibrating as it moves through space. There will be a magnetic field that forms perpendicular to it as well. And so you have a magnetic field and you have an electric field. And as that charged particle moves through space, it'll disrupt the electric and magnetic fields. And that is called an electromagnetic wave. So here's a better illustration of it, where you have the electric field vibrating up and down, and then perpendicular to that, you have the magnetic field vibrating. And that is an electromagnetic wave. Now, there's several electromagnetic waves, and you should know them in order from smaller wavelength to larger wavelength, or vice versa. And remember that wavelength and frequency are inversely proportional, back to when we talked about waves. So if you have a small wavelength, then you have a high frequency. And if you have a large wavelength, you have a low frequency. And those electromagnetic waves consist of our lowest frequencies, which are radio waves, which range in wavelength of 700 to, somewhere on the centimeter to meter range. Radar is in centimeters, TV, AM and FM are on the order of meters and hundreds of meters. And then the next highest frequency is infrared, which is just a little bit longer wavelength than red light. So notice that UV is on the other side of visible light. Notice how small visible light is of the whole entire spectrum. And considering that we view the earth and the world and perceive the world using visible light, the idea that it's just such a small part of the spectrum is kind of, overwhelming if you think about it. But we are so dependent on visible light to perceive, the world around us. But there are other wavelengths of light that actually, are just as important. And some animals see in them. For example, wolves and dogs see in the infrared. We don't see in the infrared. And bees see in the UV. Okay, so the next highest are X-rays, and the next highest frequency, the highest frequency of gamma rays, which is radiation. And obviously, as you go this way, you get more and more energy, right? These waves have more energy, and thus they are more harmful. Now, it turns out that the type of wave is not determined by the wavelength. Just like in sound, if you had a note of 440 hertz, that would be the note C. In light, the frequency in hertz defines the type of electromagnetic wave. So how do we figure out that? Well, it turns out that all electromagnetic waves travel at the speed of light in a vacuum or air, and it doesn't matter whether it's visible light or ultraviolet or radio waves or gamma rays. They all travel at 3 times 10 to the 8th meters per second through space. And remember that speed is equal to lambda f, and if the symbol for our speed is c, then c equals lambda f. So if I know the wavelength in meters, and I know the speed in meters per second, then I can figure out the frequency. The frequency is going to be the speed of light divided by the wavelength in meters. So, for example, if I wanted to find the frequency of a wavelength of light that's 800 nanometers, it's going to be 3e to the 8th meters per second divided by 800 e to the negative 9 meters. So once again, you got to know your prefixes in this course. So if I put that in there, it's 3 exponent 8 divided by 800 exponent negative 9, and I get a frequency of 3.75 e to the 14 hertz. If I do 80 centimeters, it's going to be 3e to the 8th meters per second divided by 80 e to the negative 2 meters. So 3 exponent 8 divided by 80 exponent negative 2 equals 3.75 e to the 8th, e to the 8th hertz, and 3e to the 8th divided by 8 meters is going to be 3.75 e to the 8th. I better make sure I get that right. So the original one was 3 exponent 8 divided by 80 exponent negative 2 is 3.75 e to the 8th. So that was correct. And the next one is 3 e to the 8th divided by 8, which is 3.75 e to the 7 hertz. And if I had micrometers, that's going to be 3 exponent 8 divided by 80 exponent negative 6, which is 3.75 e to the 12 hertz. Now, to identify what type of electromagnetic wave, we would need to know the frequency range. So we're going to look for a frequency range of 10 to the 14th here, 10 to the 8th, 10 to the 7th, and 10 to the 12th. So let's pull up a better chart that gives that to us in frequencies. Okay, looks like this does it. So put that up. So if we blow this up, we see that 10 to the negative 12th is a gamma ray. So on our document here, 10 to the negative 12th would be a gamma ray. But we need 10 to the 12th. And actually, oh, these are wavelengths. Oh, that's my bad. Okay, not the best one. Sorry about that, guys. Need to find one that has frequencies on it. Here we go. All right, frequencies here. So 10 to the 12th is going to give us infrared. So 10 to the 12th is in the infrared range. 10 to the 8th is in radio waves. 10 to the 7th is in radio waves. So 10 to the 12th is infrared. 10 to the 7th and 10 to the 8th is radio. And 10 to the 14th is right here in the middle. And it's in between infrared and ultraviolet, so that would be closer to visible light. Now, it's important to know that as these wavelengths of light go into another medium, they are going to slow down. The fastest they will travel will be in space. They slow down by to 2.9999999 e to the 8th in air. And then if they go into any other material on Earth, like water or diamond or plexiglass or oil, they will slow down even more. But their frequencies are constant because that's what's defining them as a particular type of electromagnetic wave.